Hi, how are you? Welcome to the lecture on fluid dynamics based on your textbook. This is a long video. It's about 36 minutes and 10 seconds. And we're going to be talking about a lot of different things on fluids. Gases and liquids are both fluids. We're going to be talking about density, forces, applications of mechanics, the flow of fluids, and buoyant force, among other things. Now, this is just simply an idea to show you the height of the fluid. Now, the pressure. This is supposed to be mercury, and it's in a eudometer. A eudometer is something that's opened on one end. It's going to be opened in the side that's in the mercury, and the top end is closed. And the area, the region above the dotted line, is going to be a vacuum. And that the pressure is simply based on two things: the type of fluid, i.e. it's mercury, and the height of the column. That's all that the pressure of the fluid is based on. Now, when we study density, for instance, we will not use D as you may have used in chemistry. We're going to be using the lowercase rho. If you know the Philadelphia Phillies, they use the lowercase rho on their uniform, kind of cartoon-like P, and we're going to be using that for density. Now, again, something else we're going to be using for density, and that is density in chemistry you studied as grams over cubic centimeters. Again, density is mass over volume. We're going to be using kilograms over cubic meters. So if you think about a big box, that's 1 cubic meter. We're going to be using the mass in kilograms over the cubic meter. Okay, now, for instance, if I have the density of aluminum is 2,700 kilograms per cubic meter, what is the mass of a rectangular piece of aluminum that has the dimensions of 2 centimeters times 350 centimeters times 4 meters? Well, what you have to do is you have to convert everything to meters, because again, in physics we only use meters, kilograms, seconds, etc. So you have to convert everything to meters. So if you convert everything to meters, and we know that from the equation density times volume will equal a mass, 2,700 times 2 meters times 3.5 meters times 4 meters is going to be 7.56 times 10 to the fourth kilograms. You're going to have to really be able to use scientific notation in this unit, or you're going to find things fairly difficult. Again, if I have a large body of water or a small body of water, the pressure is rho GH, and that is simply that it's the density of the material, i.e. water or mercury or etc., times the height or the depth of the fluid times the acceleration due to gravity. So I suppose it's going to be similar to potential energy. We'll talk a little bit about that as we go through here, but it's just simply based on the nature of the material and the height of the column, and of course the acceleration due to gravity. You double the depth, you double the pressure. I think that's really what we want to get across here. Pressure equals the density of the fluid times G, which is 10 meters per second squared, times the height of the column, and that is represented by rho equals pressure P equals rho GH. Now, something very, very important, and that is that the density of water is kind of the standard with density. you studied in chemistry that it was 1 gram per cubic centimeter. Now we're going to understand that it's 1,000 kilograms, 1 metric ton per cubic meter. And 1 Pascal, named after a scientist, 1 Pascal equals 1 Newton per square meter. Again, think of that 1 cubic meter box full of water that will weigh 1,000 kilograms or 1 metric ton. Again, it doesn't really matter the shape of the column. The pressure, again a vector, is going to be the same for all of them. It's simply based upon the height of the fluid. Just let me go back a little bit for a moment and think of that. Try to picture a 1 cubic meter box, 1 meter tall, 1 meter wide, 1 meter deep, and that cubic volume, if you fill that with water, that will weigh 1,000 kilograms or 2,200 pounds or 1 metric ton. Very important. Now, when we talk about pressure, this is the Burj Khalifa. Actually, next year I'll be living not too far north of this building. This building is a half a mile tall. And it has to be, the plumbing has to get up to the top of the tower. So you have to use a counterforce in order to get the water up there. It's twice the size. It is twice the size of the World Trade Center. The World Trade Center was a quarter mile tall. This is going to be a half a mile tall. Unbelievable. And you have to talk about hydrostatic pressure. Hydrostatic pressure combines just the regular atmospheric pressure, P sub A, and the height of the water column. So it's going to be a half a mile high, plus you have the atmosphere as well. So you have a lot of pressure on this fluid that you want to get up to the top of the Burj Khalifa. Atmospheric pressure is newtons per square meter. That's air pressure. Additional fluid pressure, newtons per square meter, is usually the water pressure. This is called hydrostatic pressure. And the height of the fluid column will be very important in this particular example. Now, remember, a Pascal, 1 Pascal is 1 Newton per meter squared. These are some other shots taken by a friend of mine who, it's hard to get the whole building up close, so it was a pretty amazing group of shots that they took. Here's another shot of it. Amazing building. And it requires a fundamental knowledge of fluid dynamics. Again, this is in the United Arab Emirates, in the emirate called Dubai. Here are some reference. You can see the World Trade Center was a little over 400 meters. That's a quarter mile. 1,600 meters again would be a mile. So you can see some of the famous buildings. The Taipei Tower. Taipei is the capital of Taiwan. You have the Petronas Tower in Kuala Lumpur, which is the capital of Malaysia. The World Trade Center. You have various other towers. So it's pretty amazing engineering that goes into all of these buildings. And again, a working knowledge of fluid dynamics is very, very important. Otherwise, you really can't service these tall buildings. If it wasn't for our knowledge of these tall buildings, of the engineering of fluid dynamics, we couldn't build them that tall. So that is pretty tall building. Now, this is a very, very important topic. This is called Pascal's principle. Now, if I put, let's say that's 1 Newton on the left, that's the input force. Again, input force. This is kind of like a machine. If I put 1 Newton device there, and let's say that is one square centimeter, and on the right the output is 50 square centimeters. Well, the pressure will be 1 Newton per square centimeter, and then I can lift 50 newtons with just one Newton. So the pressure is going to be transmitted throughout the liquid. I'll explain a little bit more of that in class. Pretty important topic. One of the major laws or principles in fluid dynamics. The buoyant force of material is the weight of the volume of water displaced by an object. Will you please imprint this on your brain? Buoyant force is the weight of the volume of water displaced by an object. The weight of the volume of water displaced by an object. I can calculate that by simply saying the volume of displaced fluid times the density of the fluid times G. So, buoyant force equals the volume of fluid displaced times the density of the material times G. Easy. Now, what is buoyant force and how does it really work? Well, as we said, the farther you go down in the liquid, the greater the pressure. So, if there is a large rectangular object, for instance, the pressure on the bottom of it will be greater than that on the top. So the forces will not be the same on it. It's not the same. So it's this kind of like gradient of forces on an object based on the depth of it, of the object in the fluid. The fluid can be either air, or the fluid could be water or anything. And so this gradient of forces based on the depth of the object in the water is going to create this buoyant force. The buoyant force is an upward force. We're going to call it negative. The buoyant force is upward, it's negative, and the downward force is weight or positive. Now, here's a picture from the text, and it clearly shows when you immerse an object, there's going to be a volume of water that's displaced, or a volume of fluid that is displaced by the object. Well, the buoyant force is going to be the volume that I actually displace based on the size of the object, times the density, times the acceleration due to gravity. So it's pretty straightforward. Now, this is something that is going to be very important. It's something that I still marvel at. If something is floating, that means that its weight is equal to the buoyant force. If something is floating, it means its weight is equal to the buoyant force. So a battleship, a giant battleship, is floating. Big, heavy, iron battleship is floating. Well, what's the weight of that ship? Well, listen to this. It's amazing. The weight of that ship is going to be equal to the weight of the water that the ship displaces. So the volume of the water displaced by the ship, that volume of water has a mass, and that mass has a weight, and that weight of that volume displaced is equal to the weight of the ship. Absolutely unbelievable. And humans are mostly made of water. So it's not terribly difficult to float, especially in salt water. And this scuba diver here is floating around, and yes, they have weight belts on, and the tank changes the buoyancy, and the weight belt changes the buoyancy, etc. But it's not difficult, even with a weight belt and a tank and all of this gear on. A human being, the reason we can do scuba diving, scuba stands for self-contained underwater breathing apparatus, pioneered by Jacques Cousteau and his family. If the human being wasn't predominantly water, then they wouldn't be able to scuba like we do. They wouldn't be able to float. Swimming would be extremely difficult. So the fact that we are mostly water will help us float. And, if you've ever been scuba diving, it's really cool. So here's a brick that's being suspended by a scale. It has a volume undetermined, but it has a weight of 3 units. Now I'm going to immerse it in a fluid, and I find that the fluid is going to be that it displaces is 2 units of weight. So the brick was 3 units of weight. The water it displaces is 2 units of weight. So what's left? Well, what's left is what we call an apparent. What's the apparent weight of the brick in water? Well, it's 1. It's not equal. The fluid displaced is not equal because the brick would sink to the bottom. But it has, you subtract the buoyant force from the weight. Now, if something is floating, the brick was not floating. Don't be confused. The brick was not floating. But if something is floating, there's no net force. The weight of the object, weight is going to be positive. I'm going to be asking you on quizzes what was the weight, and it has to be listed as positive. The buoyant force is going to be negative. That's the standard we will use. Your physics teachers in the future may use a different standard, but that is what I will grade you on. That is what you will be held responsible for, because force is a vector. So for those forces to be equal and have no net force, that means that the object in the fluid is actually floating. Remember, that fluid could be a gas, like a balloon floating, or a battleship floating in the sea. This is another shot of various forces. Now, the length of the arrow will indicate the size of the force. So the ones at the bottom will be greater than the ones on the top. And if you summed all of these various forces, up and down, left and right, etc., the sum of them would be an upward force, a negative upward force, and the sum of all of these forces would, this is a very oversimplified picture, but it gets the point across. The object would be have a buoyant force equal to the sum of these forces, and that would be an upward force or a negative force. So very important to understand the picture involved here. Now, what's going to have more buoyant force, that rock at the top, or the giant log? Well, remember, the wood floats because it is less dense than water. The rock sinks because it is more dense than water, and the fish floats. The fish neither rises nor sinks because it has the same density as water. Well, okay, fair enough. But what has the greater buoyant force? You'd think floating, right? It's kind of like, well, in terms of the wood, the fluid that's displaced, the weight of the fluid displaced equals the weight of the log. But the more the fluid the more the object displaces the fluid, the greater the buoyant force. It doesn't mean it won't sink. Like the canoe, very little water is displaced because the canoe is light. So just because it floats doesn't mean it has the lower buoyant force. What ship is lighter in this particular case? Is it A or is it B? Well, why don't you try to answer that and ask me in class? Try to figure it out, or ask me in class. What the answer is. I hope it's obvious to you. Remember, the weight of the volume displaced, of fluid displaced, will equal the weight. So which one's heavier? Which one's lighter? So I'm not going to tell you. I hope that the answer is pretty obvious in that particular instance. Now, the next slide is actually a bit of a doctored photo. I think it's like 4 different pictures. Oh, it's all over the internet. And it's about an iceberg. Now, an iceberg is made of ice. Well, when water is at its most dense, it is 4 degrees Celsius. So when it freezes, it becomes less dense. So the percentage of ice out of the water is roughly 10%. Roughly 10%. I think it's a beautiful photograph. It certainly may be doctored, but it certainly tells a story that is no lie. But again, the immense amount of fluid that this iceberg displaces is equal to the weight of the iceberg. And these icebergs can be monumental. They can be the size of a giant state in the United States. They can be country-sized, some of these icebergs. Enormous icebergs that break off. Especially with global warming, you'll see it much, much more. Now, this is a rule. If an object floats, the weight of the volume of the fluid displaced equals the weight of the object. You'll hear me repeat myself 1,000 times in this unit 19 and 20. But in reality, I would say, of everything mentioned here, I'd say it's probably the most important of all of the concepts that we will learn. We talked about Pascal's principle briefly. We'll talk about that more in class. I encourage you to read in the chapter. We'll talk about something called Bernoulli's principle, which is also very important. But this thing on buoyant force, gosh, it's just incredibly important. Now, I have another slide on buoyant force, very simple, very similar to what we've been talking about, and that is that if I sum all of these force vectors, I'm going to come up with the buoyant force. That picture kind of tells it all, that buoyant force tells it all. So the buoyant force is the upward force the buoyant force is the sum of all of the forces, and those forces are vectors, and they change depending upon the pressure and the depth of the object in the fluids. If it's floating, like the 2 ships above, then their buoyant force equals the weight of those particular ships. Now, something that might be confusing to you, and iron, 1 kilogram of iron, 1 kilogram of aluminum. The iron has a density of 7,894 kilograms per cubic meter. There's that cubic meter again. Very important. The density of aluminum, 2,700 kilograms per cubic meter. The volume of the aluminum will be much greater than the volume of the iron. Therefore, let me see, the volume is greater. Okay, the volume is greater, so the buoyant force is going to be greater. And why is that? Well, so this is a really good visual that the aluminum will have a greater buoyant force because it has a greater volume. It's still going to sink. Hey, it's going to sink. The buoyant force, if its buoyant force is less than the weight of the object, hey, guess what? It sinks. So here I have balsa wood, for instance. Very light density. Very little volume is displaced. Very small buoyant force. Well, why is it small buoyant force? Because it's very light, which has a greater buoyant force. The very high density metal at the bottom of the ocean, or the very low density balsa wood. The metal has the greater buoyant force. It has a large. It's a big piece of iron, but it has a greater volume. Is displaced. Displacing a greater volume of fluid because it's actually completely immersed, where the balsa wood is mainly floating. Next thing we're going to talk about is Bernoulli's principle. Bernoulli's principle is actually quite simple. Bernoulli's principle is when water speeds up, or when a fluid speeds up, when it flows through a narrow pipe, the close together streamlines indicate increased speed and decreased internal pressure. The pressure is going to decrease. The bubbles are bigger in the narrow areas because the internal pressures are much less. So if you blow on a piece of paper, it's going to rise. Why? Because the pressure is less on the paper. What does that mean in terms of flight? Now, make sure that I'm going to do a video, a clip on flight. Make sure you see that as kind of a corollary to all of this. Well, you can see on top of this wing, there's going to be a reduced pressure. Well, if you have two, let's see, one on the third line on the top picture, you have the third line, you have a molecule there, and then on the fourth line right above it, you have a molecule there. So let's say the molecules are not moving, but the wing is moving through the molecules. They're going to go from the front of the wing to the back of the wing in the same amount of time. Yet the one on top will go a farther distance. Well, hey, it goes a farther distance in the same amount of time. What does that mean? It goes a farther distance, same amount of time. So that's something that's kind of significant that you're really going to want to look at. Bernoulli's principle is no joke. I'm going to do separate video lectures on Bernoulli's principles, Pascal's principles, and also buoyant force. Now, just keep in mind this: that the buoyant force, the Bernoulli's principle says that when you have you have increased flow of a fluid, the pressure decreases. So look, you have a hose, and you don't have a hose running, and you get the hose gets very tight, a lot of pressure. The pressure, what we said, is called backs up. Well, you let that flow. You let the water flow through that. It reduces the pressure. Well, what's going to happen to the roof of this building if the pressure on the roof is less? What's going to happen when you have this giant tornado with all of these winds? I mean, tornadoes can be absolutely unforgiving. You saw the movie Twister where that barn comes apart. Well, that barn comes apart because you have increased flow of the fluid, and that's going to decrease the pressure. So when I was a kid and I was in high school, there was a tornado in Xenia, Ohio. It was sort of near Dayton, Ohio. My brother was at the University of Dayton, and he did volunteer work cleaning up Xenia. And get this, if I recall correctly, it was like a mile wide or a half a mile wide, and Xenia was just completely flattened. Look up Xenia for some extra credit and write a little bit of a report on Xenia, the Xenia tornado in Ohio in the 1970s. Maybe do a PowerPoint presentation on that. I'll give you some extra credit. Well, there's a shot, a great shot. Unfortunately, it shows death and destruction. My apologies, but it shows the devastation that a tornado can wreak upon. Now, remember, tornado is fluids, is air moving, and that creates reduced pressure on horizontal surfaces, and that reduced pressure, well, things are just going to become airborne. There's nothing holding the roof. What holds your roof on your house? Well, nails, of course, etc. But what about the air pressure that is coming down on top of you? That's also very significant. Very significant. I'm also going to do a separate lecture on water pressure and air pressure. So this is just the first general lecture for you to look at. Now, this is a description of Boyle's law. Robert Boyle was an English physicist, chemist. He was actually part Irish. And it says that if I have a constant temperature, now temperature is based on the number of collisions. So the number of collisions going from left to right are going to be constant. I'm not going to change those collisions. The number of collisions are going to be constant, right? The temperature is going to be constant. So the pressure, though, if I decrease the volume, what's going to happen to the number of collisions? What's going to happen to the pressure? It's going to increase. So I'm going to decrease the volume. I'm going to increase the pressure. So that's going to be an indirect relationship. Now, Charles' law, which is under constant pressure, examines temperature and volume. What happens when I increase the temperature of a volume of gas? Well, the volume's going to increase. Look at a balloon. I take a balloon and I put it in an oven. Now, it's a magic balloon. It won't pop. But what's going to happen to the volume of the gas in the balloon as I increase its temperature? Well, it's going to increase. So those are two laws. Also, there's Gay-Lussac'e's law, which looks at pressure and temperature, which is very similar to Charles' law, but with volume constant. Wait, if I put a can of beans on the stove and I don't open it, what's going to happen to the pressure inside that can when I heat it? Well, boom, it's going to go boom. So the three major laws that we're going to be studying are the Boyle's law, where pressure and volume are indirect. Robert Boyle, those are his birth dates. He was a 17th century natural philosopher, chemist, physicist, and inventor. Charles Jacques Alexandre César Charles. He was a French inventor, scientist, mathematician, and balloonist. Actually, Gay-Lussac got a lot of his work published. A lot of Charles' laws was unpublished, and Gay-Lussac very kindly published his works and gave him credit for things that he also discovered. Gay-Lussac was also a French chemist and physicist. Long time ago, gases was a big topic in the 17th and 18th centuries. Again, Boyle's law is an indirect relationship. Indirect, remember the product constant indicates an indirect relationship. As I increase the pressure of a gas, temperature is not an issue; it's constant temperature. As I increase the pressure on a volume of gas, I'm going to reduce the volume. It makes perfect sense. When I taught chemistry, gas laws, my students did, Some of their best grades all year were on gas laws because it makes so much sense. Gas laws is not chemistry, it's physics. Why do we study gas laws? Because you have to understand the physical nature, the physical environment when you perform chemical experiments. There's physical environments that have to be accounted for, and much of the physical environment in which a chemical reaction is taking place has to be known. The physical environment, much of it is in gas, the gaseous phase, as well as the aqueous or water phase. This is Charles' law. Quotient constant represents a direct relationship. The Gay-Lussac is pressure and temperature. Again, the ratio of pressure 1 over temperature 1 equals the ratio of pressure 2 over temperature 2. And in Charles, the temperature ratio 1 equals the temperature volume ratio 2. So that's your lecture. Study well and look for the next lectures on gas laws and Bernoulli's principle. So I'm going to publish. What I'm going to do is I'm going to publish several lectures on fluids. That's the first general lecture. It's going to be about 37 minutes by the time I'm finished. So good luck and study well, and we'll talk again.